Hello, and welcome to Learning from Nature, the Biomimicry podcast with me, your host, Lily Ehrman. This series is all about highlighting biomimetic and bio-inspired companies that are leading the way in helping to create a life-friendly future with nature as mentor and measure. I want to showcase the people doing the hard work of translating nature's genius to human design, and ultimately celebrate the potential of this field. ECOncrete creates sustainable concrete products for coastal and marine infrastructure projects and won the Biomimicry Institute's Ray of Hope Prize in 2020. Their technology addresses the chemical composition of concrete as well as its micro and macro surface. EConcrete's modular structures support the growth of organisms like oysters, corals, or barnacles, which act as biological glue, enhancing the strength and durability of structures and adding to their stability and longevity. The growth of these organisms also acts as a carbon sink, offsetting some of the huge carbon footprint associated with traditional concrete. EConcrete's technologies are cost competitive to traditional large marine infrastructure projects since they increase in strength over time, restore native habitats, and reduce mitigation requirements. My guest, Dr. Ido Sella, is a world-leading expert in ecological engineering and environmentally sensitive designs of coastal and marine infrastructures. He is the co-founder and CEO of EConcrete with over 20 years of experience in the fields of marine biology and ecology. With EConcrete, he has led implementation of ecological marine construction projects in over 30 countries for city, state, federal, national, EU, and NGO stakeholders. Ido holds a PhD in zoology and a master's in ecology and environmental quality from Tel Aviv University. I'd love to kind of start with you introducing yourself, how you got into your role.
Okay, so hi, my name is Ido Sella. I'm the CEO and co-founder of EConcrete. I'm a marine biologist and focusing in the last 15 years, even more on the impact of coastal construction and marine construction on marine life. That was our starting point when we funded this company, EConcrete, together with my friend and co-founder, Dr. Shomit Finkel. Both of us stepped out of the academy after working on different types of infrastructure in the academy, from artificial reef to pier piles, to jetties, to breakwaters, to oil rigs. And when we stepped out of the academy, it was because we felt that there is a kind of a gap that needed to be closed between the knowledge that was generated by science and that was kept within publication and going between discussions, and didn't basically trickle down into the industry. At the time, we called it responsible marine construction. So how can you reduce the impact? How can you minimize your environmental impact? But with time, we started to understand you can actually harness infrastructure to provide you with ecosystem services. Mm-hmm. And that's when we started really to focus on concrete, just because it's the most common material for coastal and marine construction worldwide.
So tell me a little bit more about EConcrete. How did this company start? Where did the idea of the company come from, and kind of how did it gain traction?
Completely by accident. Really, like truly, completely by accident. At the time, we were really focusing on the impact of coastal construction, but we surveyed and did monitoring and provided some, analysis on the performance of different types of structures. So we work with ports and desalination plants and other infrastructure that have basically some kind of an interaction with the water, so in different levels. And for us as marine biologists, it's the work was, we worked a lot on concrete infrastructure. At the time, we didn't understand that because for us it was like another port. But with time, you're starting to see that you basically spent most of your time on serving and understanding concrete infrastructure. And when you dive into the data, then it's out there. Like 70% of coastal marine infrastructure worldwide are concrete based. And for us as marine biologists, concrete was usually associated with a negative impact on the marine environment. So it's usually had low biodiversity, dominance of invasive species, also some effect on the water quality, specifically in basins because of the lack of specific filter feeders. And it was the aha moment was actually one of those surveys that we did an underwater survey on a power plant. and on a very long jetty. And we do the standard biological monitoring of different, putting transects and quadrats and analyzing and counting the species and the cover of the species on the area. And then at a certain point, we got to a section and it was a completely different what we call biological image. So it was a completely different community. Suddenly we saw species that you usually don't see on infrastructure. We saw better cover. We saw species that are very sensitive to the quality of the substrate. And it was like it jumped on both of us. Like both of us noticed that underwater. And when we came out of the water, then we discussed that and at the time it was there was a project manager. So it's infrastructure. It's a facility that's really well controlled and we reached out and we were stepping on the pier as we came out of the water and said, from this line underwater to this line underwater, we saw a completely different biological community. What is it? Like there's an outtake here or something. Like what's the difference?
That's different. What's different?
And he said, it's the same section as all the sections, both sections from both ends. But the only thing that I can tell you that the line that you described on the pier, this is a casting day. So that's the section that was casted the same day. So there's like separation between when they casted those huge pier, they did a casting and then they finished the casting one day and then the truck came the other day and did the next section. So that's a separation. And I said, okay, so maybe it was a different type of concrete. Maybe something else was poured in that affected the biology. He went. One of the benefits of working on a very controlled, there was a power plant, so they had the records of construction, and we were like waiting for this, for him to come back and say, yes, it came with the different materials and it's completely different. And he said, nope, it's actually the same. It's exactly the same as the concrete that was cast. It's according to the standards of the concrete that cast the day before, the concrete that was cast the day after. And that was the point that we said, so maybe there was like subtle changes with the concrete that is affecting the biology. Maybe you can do some changes to the concrete that is not affecting how you describe it structurally, but will affect its biological performance. And that was the starting point. So we started doing small experiments in the lab, and we started to do small experiments in the water, in the beginning in the Red Sea, in the Mediterranean, and then later on we extended that to the east coast of the US, from tropical water to temperate water, and that was the starting point. And it's so everything started completely by accident.
So what makes the ECOncrete product more sustainable and bio-friendly? I want to kind of get into the specifics about both the material itself created that encourages and invites marine organisms to settle and colonize. What makes it unique and different than other alternatives on the market?
So in order to discuss this, we need to go back a little bit to what we call biology 101. When we're looking at any sessile organisms, most of them are invertebrates that are basically colonizing a substrate underwater. And it can be corals or barnacles or oysters or bryozoans or others. All of them has a phase, or most of them has a phase in the plankton. When the larvae is basically released to the plankton or created in the plankton, and then it's basically floating around in the plankton. Usually they have a capacity. There's some kind of a moving capacity at that phase and a sensing capacity. So the larvae of a coral look like a small worm that is actually moving in the water column. The larvae of the barnacle look like a crab, like a larvae, like other larvae that are coming from crustaceans. So, and they're sensing the substrate. So they're interacting. So the currents are pushing them on a substrate. It can be a reef, it can be a rock, it can be a pile, it can be a wreck. And this little larvae is basically sensing the substrate, because when this little larvae will decide to attach itself to the substrate, this is a one-way ticket. They cannot reattach themselves. When a larvae of a coral is attaching itself and decided to what we call the colonization process. So they attract the recruitment process. Sorry. So when they basically attach themselves to the substrate, they're going through metamorphosis. And from being a little worm in the water column, they're becoming a small polyp, which is the start of a coral. So, and that's in most cases, it's a one-way ticket. You can't reverse that process.
No, go back.
So there is a process of them sensing the substrate. and they're getting different indication from the substrate if it's good for them or not. So we know from experiments, and it's there's a wide body of literature about the different materials have different what we call recruitment capacity, and so that they can be better for recruitment, and it's not even related to the, let's say, the complexity, the roughness of the surface. Like glass, for example, smooth glass is an amazing material for recruitment. But that's the main problem with concrete for marine use. So concrete that is used, that's the starting point. Starting point is that concrete that is used for marine construction, that need to be very strong and tolerate and in line with the standards for coastal and offshore construction, is not just sand, cement, and aggregate like we are perceiving concrete. It's basically a chemical mix. It's chemical soup of different components that are added into the mix in order to increase their performance, to make it stronger, to make it to stand freeze and thaw processes, compression forces, to dry super fast, to cure, to different factors. And those components are basically actually reducing the capacity of the concrete for marine construction to support marine life. And the best example that I usually give is if you walk around your neighborhood and there's a new building that was cast in concrete, how long it's going to take for that concrete wall start to grow and support mosses and lichens. So you're usually going to see mosses and lichens only on structures that are what we call towards the end of their service life, after they've been out there for long enough to have a kind of a washout and a neutralization of the surface that allow mosses and lichens to grow on it. So it's exactly the same process that's happening in the marine environment. So,
and is that because of the chemical composition or the texture or both?
No, the recruitment is basically because of the leaching out of different components that you need to control. The first thing that we did when we developed the technology was dealing with the leaching out of those components and how we address them. And you need to address them in a very specific way. And once we address them, we're basically neutralizing the surface. So it's not that you're creating a kind of you're not putting a fertilizer or something that will attract those larvae to settle on the concrete. You just knock out those different elements within the concrete that are negatively affecting the recruitment process. So let's say you do that, and we did that, and we proved that we have several papers that we're proving this on lab tests. Okay, so we collected larvae and planalies of corals and barnacles and bryozoans, and we took them to the lab, and we had small beakers where we had smooth concrete blocks, and we grew those larvae in those beakers for a week or so, and we calculated and we saw and we photographed how they go, the metamorphosis on the different blocks, and we scientifically proven significant difference between different treatments. But then when you test this in the water, in the sea, what you're usually going to see a lot of recruitment happening in the first few days, in the first few months, and increasing biodiversity, but then you'll see a drop down. Then you'll see the die off. And why do you see this die off? This is related to the rugosity, to the surface complexity. So when the little larvae is recruited into the substrate, the different effects of now we're not dealing with the recruitment process, we're dealing with the survivorship. And in order for that little larvae to survive, it needs to have a certain set of environmental conditions that will allow it to thrive and to grow. And for example, if there's going to be a terraphology growth on that larvae, she will die. And if there's going to be sedimentation or predation or abrasion forces from sand around, then it will not be able to survive. So you need to create those micro niches in the substrate that will allow the larvae, the lucky larvae that settle on the overhang, the small overhang or the small pore or the cavity that you created, basically, and it's more protected, and you increase their chances to survive. So that's basically what we do with ECOncrete. The secret of ECOncrete is how we do all of this without affecting structural performance, while we're still in line with all the very strict standards of marine construction, which are it's a very liability-driven industry, very conservative. Infrastructure are built in the past where they were built for 30 years. Now they're already built for 60, 90, 120 years design life. And we're incorporating those projects. So the decisions that are taking now are going to affect very long time. So the developers and the engineering firms are very, 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 very cautious about how the changes that they put and anything that they put in. So you need to verify and be in line with the standards. And so that's what we created. We created a package that the industry can use. It can be implemented on load-bearing pier piles and bridge foundations and breakwaters and others. With time, what we started to develop are also solutions. And this is maybe more related to biomimicry, because you can build a breakwater from concrete blocks, and you can modify those blocks with ECOncrete technology, and you will significantly increase biodiversity, and you reduce the dominance of invasive species, and you can do that. But you're still going to lack different characterization characters, or let's say factors that you can find in natural rocky shoreline, shoreline. So you won't see water retaining elements like tide pools and rock pools, overhangs, underwater caves, and other like places where you create the habitat that is basically together is defining the macro habitat. And what we did is we started to basically provide solutions that you, instead of building your breakwater from standard blocks, let's build it with a block that have the capacity to increase recruitment and increase biodiversity and a better cover, but also will provide a specific morphology that is usually missing from this structure. So we started to develop those solutions for breakwaters and seawalls and other, when we can retain water, we can create overhangs, habitats that are needed for fish, for juvenile fish, for larvae, for others, and incorporating them into the construction in a way that is completely in line with the standards. So as biologists,
that's amazing.
We address the issues of making sure that when you batch the concrete, it's not taking longer, and the people on site will be, you can use the same workforce to cast and the concrete, and you can install it at the same time, so it will not increase the working effort, which will increase cost. So all of this, and creating a package that can be easily digested by the industry. And that's the main goal that we develop.
And it's so important for that industry, like you said, because it is pretty conservative and they're doing these long-term plans, and you have to find a way in where it makes sense financially and workforce wise and timeline wise and everything. But this brought up two things that I want to kind of go back and touch on. You mentioned this idea of like structural integrity and habitat for organisms. In my brain, that looks like a block with a bunch of holes and maybe like divots. Can you explain more like how you optimize both structural integrity and habitat availability?
Sure. So let's think of a seawall in a port, like a smooth concrete wall that extends from the pier, from where the cranes, and down into the water and into the mudline. And this smooth concrete structure has different elements that need to be in compliance with. So first of all, there's a steel inside the rebar, but it needs to have a sufficient cover of concrete on it to protect it, so chlorides will not penetrate from the water column and get to this steel that is inside the concrete, and this steel will start to corrode. And basically, a corroded steel is increasing volume. It's 5 times in volume than clean steel. So it's basically breaking the walls from the inside out. So it's popping the concrete. So that's the reason on old seawalls you see those drips of rust that is coming from cracks in the concrete. So first of all the walls need to be in compliance with this. So you need enough cover of concrete on the rebar. Then you need to withstand forces. So you have tugboats and you have vessels that are docking in this port, and they are scraping the surface. Then you have big fenders that are there, and there are cables, underwater cables, that are running there and are attached to those seawalls. And this seawall was built for 30 years design life, which means you don't need to maintain it for 30 years. So you need to be super strong and to withstand all those hundreds and thousands of vessels that are going to bang on it. Now, let's say, okay, we want to create a habitat. So I want to change the complexity of the seawall. So instead of being a smooth seawall, think about a seawall that we want to create. We change the rugosity of the surface, so to create a complex surface. So a complex surface is also very sensitive. So if you create a design, a small of indentations or things that are protruding out of the, if they're going to be banged with a tugboat, they're going to break. And it's not just that we're going to lose this complexity with time because it's going to scrape with every vessel that's going to bang on it, but it's also going to affect the biological community that's going to grow there, because in biology we have a process called successions. Succession is when there is a die-off and then the community is starting to develop again. So there's the first settlers, which are the first species that are settling them, and they create the habitat, and then on top of them come the second settlers, which can be the oysters or the others, and then slowly you get this community of sessile community starting to grow. So if you break it every time and you're basically taking it back to the starting point, so you will not get to the point that it's getting fully matured. It's all the time under stress. So for me as a biologist, I want to create the most stable habitat on anything that we create. And for the engineers, it's the same. So how do we create a complexity on those surfaces that will be in line with freeze and thaw processes and ice that's scraping in the port and vessels, which means that as biologists, we have the same number of concrete specialists, coastal engineers, marine engineers, product designers in the company to make sure that when our clients are basically specifying ECOncrete for port, now we're doing the port of Rotterdam, and the design is 120 years design life.
Amazing.
Which means whatever you install need to show that it will withstand the predicted forces in the next 120 years. And I think that's the most important thing for biologists to start to understand, that in order to push for sustainable development and to understand that we are working in a world which is under stress in terms of edges, right? We have sea level rise, increased storminess, processes that called, we describe them as coastal armoring or coastal hardening and coastal squeeze. We take all our sloping shorelines and we make them vertical. So we're squeezing the intertidal area on the vertical surface. So we need to understand we need to find ways that we can incorporate sustainable development into those structures that we're going to see more and more, in order to keep some of the ecosystem services that we're losing by this coastal development. So in order to do this, biologists need to bridge this gap to the industry. And that's what we're actually doing in ECOncrete. And going back to biomimicry, so that's the biomimicry point. That's where you're starting to look. When you get to this point, you start to understand that you need to use biomimicry. And the reason is that the structures in nature are the most efficient in the balance between performance and strength. So that's, if you look at our coastal system, we have a coastal system that we use for our high performance breakwaters. And it looks exactly like zooids of a bryozoan, which is a sessile organisms. And the way that we created them, and it's the most efficient way, and the way that they interact between themselves, and the ratio between open cavities in them to strong piece. So it's really it's really look the same. So you look for those morphologies that you will see in nature because they are the most efficient. They are the one who went through the process and were proven to be the most efficient. The strength of a Nautilus shell and others. So you use it all the time, and we are utilizing it all the time. So you can see those elements in different designs that we do, just because it's the most efficient structure. And if you want to create a structure that will be strong and complex, then that's basically the easiest way to find those structures.
Are you excited about the potential of biomimicry and want to begin your own journey in this field? Take the short course set from Learn Biomimicry and kickstart a nature-inspired future. Use my code LEARNINGFROMNATURE, that's all one word with no spaces, to save $60 when you purchase the Biomimicry short course set. Just head over to learnbiomimicry.com/learningfromnature. I would love to hear how you define biomimicry and how you introduce it to potential funders if you even introduce it or if you don't really mention it. I'm curious how you approach that conversation. Perhaps it depends on the audience or who you're talking to, but how you talk about biomimicry and how you kind of outwardly project the biomimicry philosophy or approach that you bring into the company.
So let's start with the end clients. The end clients at the end doesn't really care.
Right.
What they want
Most
is the
of the
most
time,
efficient.
yeah.
Exactly. They want the most efficient solution. They don't care if it's what's the source of process. There are others that are more interested in the processes and to understand the backstage work. Then of course then you share that. But the end client want to make sure that you tick the boxes, right?
Mm-hmm.
So it will be strong enough, with in line with the standards, in compliance with their needs, and all other financial and others. But in order to get there, you as a company or as a technology need to make sure that you do that. And biomimicry is actually for us, it's a kind of a template of how to tick some of those boxes. Now, how do I address and how I define biomimicry? It's more than taking inspiration from nature. It's mimicking nature and mimicking different capacities that we find in natural system, and see how can we integrate them to industrial processes. And for us, it's very simple. But basically, what we do is we're really at the design level, right? We use most of our biomimicry is coming from the design level. So we look at structures that withstand unbelievable forces of a hurricane and flooding and tidal changes and currents, etc. And it's the best lab, what we call physical lab, that you can find, right? If you can see a mangrove forest that we stand at a hurricane, level 5, and it's still in 90% capacity, the same, more or less the same volume that he had before, which means it was efficient. And if you look at the nearby port or an unprotected shoreline, sandy shoreline that was completely eroded, you can see the difference. So you understand that something happened there that worked.
Mm-hmm.
And when you can see an oyster bed that is getting covered with sand, on a sandbar that moved in a storm and then survived after it was completely buried for 3 or 4 weeks, then something in the way, something did that. So it's first of all is understanding what's your question and try to capture this snapshot, because otherwise on biomimicry you can go all over. So for us, it's really, we're starting with a question, right? We want to find something which is the best the most efficient in. How can we solve this? And then there's usually what's happening. It's a very natural process in our company. It's not something that we're like dictating. Now we're doing a biodiversity workshop or something. You will see that the biologists are throwing something at the engineers or the designers, and then they start to dig in on databases. And then there is some type of kind of a test that we do, initial test that we do, either in our labs or in other labs or work that we do with other research institutes or universities. And it's a natural process, but it's starting with an observation, with a very straightforward observation. And we had that, as I said, on the morphology of organisms, and we had that on the morphology of natural rocky shorelines, and we did that on. We had a beautiful project that we tried to increase the ecosystem, basically built an ecosystem service package for a chain of breakwaters in the US, in protecting the tip of Staten Island. And at that point, in this region, we're really very focusing on oysters, on the eastern oyster, which in the past was one of the most common species in the area, and it's not like that anymore. And it was, what are the morphologies that will basically induce recruitment of oyster spat? And then, what are the morphologies of the mature oyster bed that if we can mimic them, we can expedite the process. So those are the question, and how can we fit that to the breakwater, and what are going to be the benefit for the breakwater, and what are going to be the benefit for the coastal protection that those breakwater need to provide. It's going are we going to find them if maybe there's no benefit? The starting point is starting to understand. So it's really the most natural process that we're doing here, and it's happening on a daily basis.
On a daily basis.
I love that you said it's like a living lab, right? The world around us. I think that's a really powerful statement, because we all are trying to solve for these massive challenges that are only going to get more challenging in the next 100 years. And the world around us has been solving for and continues to solve for a lot of the same challenges, and peering into how it works is part of our future. And making sure that those designs tick the boxes and are just as competitive, if not more competitive, than the alternatives. This is a theme that I've seen and heard from folks who are running successful biomimicry companies. They're making products that are more competitive and more efficient, and maybe not cheaper yet, but will be cheaper in the long run, and they're able to model that and showcase that. And I think that's a really powerful use case for biomimicry, right? Like, how do we solve a challenge, and looking to nature to more efficiently solve it than the conventional alternatives? And I'd like for you to speak to how those challenges are going to get more challenging in the next 100 years, and why we need breakwater and coastal habitats like this, and where you see ECOncrete kind of fitting into those solution spaces.
I want to touch on something that you said before, because it's really to the point. Those solutions that come from biomimicry will be, most of the time, will be more efficient than others. They'll be more resilient. They will be more energetic, efficient, or other. But most of the time, they will not be more cost effective at the one-to-one comparison, right? So a wing of a plan, of a standard plan, or a wing that was modified with an extra tip that came from biomimicry, there's going to be a cost difference. That just because maybe more material is going to be used, or different processing to be run on this, or other things. Because naturally, what we have now in the industry is the most cost effective, or most of the time is the most cost effective, low hanging fruit that is available.
Yeah, especially within the systems that have existed previously, that they're currently controlling what can get to market, what's cost effective, all that sort of thing. Exactly. Biomimicry definitely goes against the grain in that sense.
So there is kind of a gap. The gap in the challenge is sometimes cost related. So how can you bridge this? So most of the time, it's not, you will not be able to reduce your production cost to fit into mass production processes that are the most efficient, and sometimes also have other impact that are neglected and you don't want to deal with. So it's going through a regulation, so regulation requirements. So for example, restrictions on CO2 emissions actually drove a lot of biomimicry solutions, biomimicry-induced solutions forward, because you need to be more efficient. So you need to be more efficient, and you need to invest funds in order to be more efficient, and that made the bridge. So it's, in our case, it's environmental regulations. So the regulators are much more educated. They know what to ask. They're putting targets to the developers. If it's a port, if it's an offshore or wind farm, or a lease, or if it's underwater cable that is running between two sites. And by setting the frame, suddenly those entities need to look for solutions. So regulation is critical in different industries in order to bridge this financial gap that it's the starting point of any biomimetic solution. And I think that's a major challenge for all, and you can see that across the board, because when you peel everything and it's beautiful, and the colors of butterfly-induced colors are more vivid and have different, but still they're going to be more expensive, and you need to create the market for them. So one is regulation, the other is education. And that's very specific to specific market. Unfortunately, I think that in our market, it's more regulation related, but there are solutions that it's about education. There's a willingness to pay for more educated and more efficient solutions. There's a kind of I think what's the sustainability revolution, and I know how to call it, but it was called in the past the green revolution, but it's not the green revolution anymore. It's a more holistic approach, and it's trickling down to the people. It's trickling down to my son and daughter, the way that they choose which clothes they buy and what are the apps that they're using, and in the different solutions which are less infrastructure or let's say government, state, city related. It's a major drive on putting those solutions and bridging the financial gap.
That's so true. And I think that is a really important reminder, because as we hope to see more biomimicry solutions in the market, it's going to have to come from both directions. And a lot of the companies I've been speaking with have been pushed forward because of regulation. And I think that's a big one, right? Like, how do we, for Amphico, which was the textiles based on structural color, the regulation was limiting PFAS in clothing, right? Or textiles. And then they were able to be a little bit more competitive. And I just hope it continues to bump that forward, because we see it, the biomimics, the naturalists, the sustainability folks, we see the potential. But until both kind of top down and bottom up are able to meet, and we're able to push these forward in a meaningful way, I think they're going to stay a small scale. And so, I'd love to hear, maybe as we kind of wrap up here, where you see ECOncrete in the next 100 or 10, 50 or 100 years, and its role in creating a resilient, climate adapted future.
So in a way, it's going specific for us. It's going back to the way that we are really the basic knowledge, the basic assumptions that we started this company, and it's responsible marine construction. So now, as we're going to see more land reclamation projects and artificial islands, and really increasing the footprint on world seas and oceans, is we need to build it in a responsible way. We need to address it in a way that will allow us to get the services that we need nature to provide us. So if there's something that I hope is, and not because of financial, where I want to see the world and us in 10, 15, 20 years, 100 years, is that there are more and more technologies that will facilitate responsible development. And it's in construction, and it's in transportation, and I think I want to be a part of this revolution, because we need, it's the same process, the same, what we're pushing in the marine construction market is true for terrestrial markets and transportation and supply chain. And we need to be more efficient. We need to address the entire ecosystem, and to see how we do all those processes that we're just going to extend, be more and more, and more even dramatic with the years, right? When we're going to see the shift, the shift that we see now in climate change, and we're probably just seeing the tip of the starting of the shift. It will call for different solutions, that some of them will be very aggressive. And if we'll be able to create a kind of a toolkit that will allow us to do this jump, it's probably in our near future, that it's similar to what we saw probably in the Industrial Revolution. There was like a quick jump of, and at the time the toolkit was not there. So that's why we see so much pollution and footprint and issues are associated with the Industrial Revolution. But if we'll be smart enough to create a toolkit in advance that will already be available to the market, then there is a chance that we can do it in a better way. And that's what I hope to be a part of.
What are some exciting movement forward? What's something that you're looking forward to either this year for ECOncrete or a cool project that you're working on perhaps that's coming up, but what's in the pipeline for ECOncrete?
So we have a
If you're
lot.
able to share.
Yeah, no, we have a very busy years ahead of us.
Yes, very, very, very busy.
There's a lot of coastal and marine development happening around the world right now. So just if you look at just in the U.S., so the investment that is done to infrastructure by the infrastructure bill, the jump into wind energy project offshore, basically is calling for around 2,000 turbines, offshore turbines, to be built on the east coast of the U.S. in the next 7 years, and this is just before the next batch on the west coast is starting. You look at what is happening in the North Sea, that most of the energy of Europe is going to come from wind energy in the offshore. So if we're seeing 2,000 turbines coming up in the US, it's 8,000 in the North Sea by 2030. So we involve, and both of them are really doing the step forward in terms of what we call responsible construction and addressing ecosystem services and the impact on the environment and putting targets. Some of them are more advanced than the other, but you see the change. You see that the same discussion in the past was 2 years ago. It was very, carbon emission driven. Now suddenly it's biodiversity driven, and which is great, because I think it's including the carbon sequestration in it. And at the same time, we see coastal, as we said, coastal protection project all over. So we have different projects. We're scaling up in terms of the size of the project we're part of, and because of our track record of the years and the science behind this. So suddenly we're getting into project in the past we never thought that we'll consider building in a more responsible and holistic way. We're also putting a lot in R&D, looking at new markets and new solutions. One of the main reasons that we started ECOncrete is because there was a point that we needed to take a decision if we're going to be an NGO or a for-profit company. Now, 10 years after, I must say that in order to create a real impact, you need to be a for-profit, because an NGO has a limit to the funds that it can deploy. Maybe it's dependent on what type of an NGO, but there's always a limit. There's always someone that will take the decision on if to stop it or control it, and there's a limit on what you can do. If you're for profit and the clients are willing to incorporate that, and you find a way to get into the industry, your impact is much more efficient and much more in size. It's unbelievable. Like we always said, if you keep the same amount of people in an NGO, and you calculate after X of years the actual impact that was happening in the water, like how many breakwater were starting to increase biodiversity and seawalls in ports, and the new species that we brought, and reduce the dominance of invasive species, then you can't even. There's no chance that an NGO could do that, because you need to make sure that you create something that the market is willing to pay for, and then it's kind of platform. So for us, the next years are divided with targets that we want to achieve, just because it's kind of the goal of the company, and the targets you want to achieve in order to, as any other for-profit entity. A lot of it is now related to offshore and the connection between the coast and the offshore. So we have a lot in the pipelines which are underwater cables, protections, desalination plants, and others, and also working in markets where the regulation is more advanced and really took the step forward, looking at biodiversity, assessing biodiversity after the construction, putting responsibility on the developers on the impact on biodiversity, even 30 years after the construction. And in different regions of the world, we're starting to see that more and more. So yeah, that's our coming years.
That's so exciting. I'm really looking forward to seeing how it expands and deepens and impacts in that space. Okay, last question, because I know we're at time. What is bringing you hope?
It's the small thing. It's when I find the time to go and dive in ports and in piers, and suddenly we can see endangered species coming back. and endemic species that were not seen before. It was the first time that we saw a heron coming, a white heron come to a forge on a project we did in the entrance channel to the port of San Diego, or when we saw the green crab in New York, up the Hudson, just in Brooklyn, that in the past were only seen in Jamaica Bay. So those small things that you understand that like they're out there, and we just didn't provide them the niches that they need, and they can be working with us and provide us, the same urban nature that we're getting from park, we can get in the waterfront in a city, and we just need to approach it. So I think those are the small wins that are always great to see and capture, and really it's what's pushed me forward and give me hope. And we had some projects that the results surprised us. Although you do this, but every once in a while you get this project when you're saying, wow, think about what, like, if you change that 3 years ago, the impact, all those aha moments, and that you're starting to see juvenile fish, and you just to see nudibranch starting to lay eggs in area when they were not seeing before, and you increase the sessile community and the immediate impact that you have on the fish community that come to forge. So suddenly the associated fish on those structures, so you can see also the impact on the water column, and to generate, I think, the science. I think that's the, we're publishing a paper every year, and it's because we're capturing so much, the data. It's super important for us to keep it in a high quality. And you have this time that you are doing analysis on the data, or you're running a statistics, and you suddenly see these things popping out. This is what gives me the energy to go forward.
I love that. And the ripple effects are so simple, but sometimes can be so powerful. That's beautiful. Thank you so much for joining me. This was really wonderful, and it was an honor to chat with you. And I'm really excited and stoked to see where ECOncrete goes next.
Thank you. Happy to join, and hope we can discuss those things more and more, because I think there is a lack of understanding of those aspects with the larger audience. I think that it need to go from the tree huggers like us, and take a step forward into the decision-making process.
Definitely. I teach undergrads, and a lot of the conversation is like, okay, we're excited about this. We love this topic, but how do I do it, or how do I make it feasible? And that's why I love having these conversations and hosting this podcast, because I get to talk to people that are literally doing it. It's possible. And it's not only possible, it's happening. Thanks for tuning in. This is a quick reminder that we have some really awesome nature nerd merch, like shirts and stickers, so you can help support the podcast and look cool on your next hike. These were custom designed by my friend and incredible artist, Sarah Williams, and they showcase the amazing range of unique organisms here on Earth. You can grab yours at learningfromnature.earth/merch. I also want you all to know how much I appreciate every review, rating, recommendation, and support, as you are all helping biomimicry reach more people. Together, we can not only imagine, but create a beautiful world with life at the forefront and guiding the way. This episode was brought to you by Learn Biomimicry. If you're wanting to start your own biomimicry journey, they have a special offer for my listeners. I've known about Learn Biomimicry for ages, and actually was a mentor for one of their programs briefly a few years ago. I've seen firsthand the impact it can have on folks. This is your chance to better understand biomimicry in just 3 short courses, all with the depth of a degree and the ease of a TED Talk. Today, Learn Biomimicry has helped more than 1,679 learners from over 41 countries practice biomimicry in their personal and professional lives. They've brought biomimicry to every continent, with the exception of Antarctica, although that could change, you never know. All my listeners save $60 when you purchase the Biomimicry short course set. There's also a free ebook to get you started. Use the coupon code LEARNINGFROMNATURE with no spaces, or head to www.learnbiomimicry.com/learningfromnature. That's all one word, www.learnbiomimicry.com/learningfromnature. Happy learning!